Okay, so it's time to begin the scientific part of the workshop. And the first speaker is Jeong Kim.
Yep.
Which I know since a long time. Actually, it's been one of my first collaborators, and via Gilsburg when the Jeong was in Calgary University, and we have a paper together, which was quite successful, I would say. But then we never had any opportunity to keep on collaborating.
Even though we are quite close.
Yeah, we're close to each other, but somehow we never managed to do that. So anyway, it's a great pleasure also like personally to introduce the next speaker, which will tell us about non-local quantum state ensembles and quantum data hiding.
Yep.
Please.
Thank you. Okay. Good morning. I'm Jeong Kim from Jeong University. And first of all, I'd like to appreciate Francesco and Juno for this chance to talk here. And also, I'm quite honored to be the first speaker of this workshop. I didn't really expect this. Anyway, today I'm going to talk about non-local quantum state ensembles and quantum data hiding. This is a joint work with my postdoc, Dong Ha, who's sitting there. Raise your hand. Yeah. Okay. And we recently put this on this archive. So you can see the details here. Okay. Okay, this is the outline. First, we'll talk about bipartite quantum state discriminations, mainly about some certain discrimination strategy called minimum error discrimination. Okay. Then we'll move to some bounds on local minimum error discrimination. And this bound is obtained by the concept of partial transposition. And we'll use this bound to analyze how the data is reliably hidden in the data hiding scheme later. Then we'll move to the quantum data hiding scheme. And for the analysis, we first talk about the concept of multi-fold ensemble. Then I'll provide the actual quantum data hiding scheme. And if the time permits, and we'll see some examples about this data hiding, then I'll summarize. Okay, so because we'll talk about bipartite quantum state discrimination, the Hilbert space we consider here is this composite vector space. And the quantum state is an positive operator with unit trace acting on this composite vector space. And the measurement is a set of positive operators with this, can you see the point here? Yeah, with this completeness condition, okay? So let's think about the situation like this. So there is a set of states from row 0 to row n-1, n states, and one of the states will be prepared from the set with certain probability. More precisely, row I will be prepared from the set with the probability eta I. Okay? Then the task of quantum state discrimination is to guess which state is prepared. Okay? So it's not like quantum tomography because the set of states together with the probability is already known to everybody. So you can just guess which one among those states is prepared. Okay, so to describe this situation, I'm going to use the notation of probability ensemble. Okay? So we're going to use the term that state discrimination of an ensemble, epsilon, that means a state row I will be prepared with this corresponding probability, and we're gonna guess which state is prepared. Okay? So of course, what we can do is to make a decision rule to determine which state is prepared. And quantum mechanically, what we can do here is to perform measurement. So we're gonna use this measurement to decide which state is prepared. And the decision rule here is like this. If M0 is detected, then we're going to guess that the prepared state is row 0, no matter what the actual prepared state is. Okay? And as we know, the probability of detecting MJ when row I is prepared is the conditional probability here. And it's, yeah.
Sorry.
It's okay. No, it's okay. So it's better. Okay? Yeah. So so where were we? Okay. So the probability of detecting MJ, conditioned on the preparation of row I, is given by this inner product of these two operators. as the promise in quantum mechanics. And the average probability of correct guessing, which is the expectation of the correct guessing probability, it's given like this. Of course, this is the case when we use the measurement, this M, okay? Of course, and the average probability of correct guessing depends on which measurement we're going to use, okay? And the guessing error is nothing but the complementary probability, which is the expectation of wrongfully guessing probability. As the expectation of probability, so this success probability is always between 0 and 1. And we know that the perfect discrimination is possible, and it's if and only if the states here are orthogonal to each other. Okay? So in other words, if the states are non-orthogonal, then we'll never achieve this perfect discrimination. So the minimum error discrimination is to perform the state discrimination, maximizing this average success probability. And the maximization is over all possible measurement. And the maximum value is also called the guessing probability. So here G is from guessing, but at the same time, you can also think like this. There is no restriction on the measurement. So we can use any possible measurement to maximize this value. However, because we are talking about bipartite quantum state discrimination, so maybe there can be some restriction on the use of measurement. So if the allowed measurements are only LOCC measurement, which can be performed by local quantum operations and classical communications, then the maximum of the success probability, average success probability of all possible measurement will be denoted by PL. Okay? So this is the possible maximum achieved by LOCC measurement. Okay? Because LOCC measurement, the set of all LOCC measurement is properly contained in the set of all measurement, so we can have this trivial inequality. Okay? PL is always bounded above by PG. And also, so as mentioned before, the probability set is already known to everybody. So we can just guess that the prepared state is the state with the largest probability. Okay? We can always do that even without measurement. Okay? So the maximum value of the preparation probability can be a lower bound of this PL. Okay? And it's also bounded below by the mean of the probabilities, which is 1 over n. So it's like this. The maximum success probability over all possible LOCC measurement, PL, is always bounded above by PG, and it's always bounded below by 1 over n, which is nothing but the random guessing. Okay? Okay, so let's move to the bounds on local minimum error discrimination. That means the bounds on this PL. Okay? So the bounds is based on the concept of partial transposition. So I guess most of you are familiar with partial transposition. So for an Hermitian operator acting on this bipartite vector space, we just take transposition partially on one of the subsystems. And we call it the partial transpose of E, and will be denoted by EPT. So as we know, the transposition depends on the choice of basis. And for the definition of this partial transposition, it also matters which subsystem you're going to transpose. Okay? However, here we are only interested in the IM values after the partial transposition, which is invariant under the choice of basis and then under the choice of subsystem to be transposed. Okay? So this the definition in the yellow box is always consistent. So for an operator E, it's called PPT, or positive partial transposition, if its partial transpose is still positive semi-definite. Okay? Otherwise, it's called NPT. Okay? So by using this concept of partial transposition, we can have an upper bound of PL which will be denoted by PG. And PG, the definition of PG is like this. For the given ensemble, epsilon, for each state rho I, we think about its partial transpose. Then think about the inner product with the measurement operators, and then expectation. And we're gonna maximize the expectation over all possible measurement. Okay? And we'll denote this as QG epsilon. Then one thing that is already known before is that this QG epsilon is always an upper bound of this PL epsilon. Okay? It always gives an upper bound for the maximum success probability of all LOCC measurement. Okay? And it's simply because of this, this is the equality inside the parentheses. Because the trace is invariant under the partial transposition. Okay? And also, although we have an upper bound for PR, it's still an optimization problem. To obtain that value, we need to optimize over possible measurement. However, we can have an equivalent condition for a measurement to realize this QG. So more precisely, for a measurement M, it provides QG. That means that maximizes that value, and it's if and only if for each I, this operator is positive, semi-definite. So in other words, for a given measurement, we can always check whether that measurement is an optimal measurement or not, simply by checking this positivity. Although it's an optimization problem, we can have some analytic form for some cases. And the case is that the ensemble only has two states. So for the case of two-state ensembles, QG can be written like this, like in a closed form. Okay? This is recently obtained result. And for a general case of ensembles, we can have an upper bound of QG. So more precisely, it's like this. For any Hermitian operator H satisfying this positivity for each I, then we can show that the trace of H will provide an upper bound of QG. Okay, so let's talk about quantum data hiding. So because we're going to use the preparation of state from the ensemble epsilon several times in a quantum data hiding scheme, so we'll think about this situation. So first, we prepare a state from an ensemble, and let's say the first prepared state is rho C1 with probability rho C1. Rho C1 with probability eta C1. Then we'll repeat this process several times. So that on the second preparation, the prepared state is rho C2 with the probability eta C2. Okay? We just repeat this L times. Then the total state of the preparation can be written as the tensor product of this state from rho C1 up to rho CL. Okay? So that's, so you can see the tensor product of the states there, right? And of course, the corresponding probability is nothing but the multiplications of the corresponding probabilities of each of rho C1, rho C2 up to rho CL, which is the product, the left-hand side of the yellow box. Okay? So for this, to indicate this, the total state, we're going to use this vector C, which is in Zn to the L. Okay, so to indicate that total prepared state, so it's like this. The coordinates of the vector indicates which state is prepared. So more precisely, the ith coordinate of the vector indicates which state is prepared in the ith run. Okay, ith repetition. Okay, and the L-fold ensemble of epsilon is denoted by epsilon tensor L, which is the set of all possible such states. I mean, set of all possible L tensor product of the state from ensemble with the corresponding probabilities. Okay. And one more thing we're going to define here is the weight of the index vector C. So for each C in this Zn to the R, we just define the modular n weight, which is nothing but the summation of all the coordinates of the vector in modulo n. That means the remainder when we divide the summation by n. Okay? And clearly, the weight is always in Zn, the set of the integers from 0 to n minus 1. Okay. So now let's think about the situation here. So from that L4 ensemble epsilon L, a state rho C is prepared with the probability eta C. Okay? The state discrimination is to guess which state is prepared. But instead, we are here just interested in the weight of the index. Okay? So rho C. So to guess the weight of the index, we don't really need to know which state is prepared. Okay? Because there are several states having the same weight of the index vectors. So it's like this. So for the multifold ensemble epsilon tensor L, we can think about its partition into subsets having the same weight of the index vectors. So more precisely, in this ith subset, maybe I can use this one. So yeah, here. So in ith subset, there are only states rho C having the weight of the index I. Okay, it's a partition and it's an even partition. You can easily see that there are n to the L minus 1 states having the same weight of the index. Okay, it's because if you can think about the coordinates here, to make this weight of this vector I, you can have the L minus 1 variations. You can just determine the last coordinate to make it the weight I. Okay. So it's an even partition of the subsets. Then we're going to further make this subset into ensembles by normalizing the probabilities in the subsets. Because the probabilities in one subset is not the probability distribution. It's not normalized. But we can normalize it simply by dividing the probabilities by the summations of all probabilities in the subset. Okay, so that here eta I, L tensor product, is a sub-ensemble of the original ensemble. Okay, so now we can think about the situation like this. The preparation of rho C from this epsilon tensor L can be considered like this. First, we prepare the sub-ensemble from this L tensor ensemble epsilon with this probability, and then we prepare rho C from this sub-ensemble with the corresponding conditional probability. Okay? And if we just want to know the weight of the vector, index vector C, we don't really need to know which state is prepared. We just need to know which sub-ensemble is prepared in the first place. Okay? Yeah, so the guessing the weight of the index is equivalent to guess which sub-ensemble is prepared. Okay, and moreover, if we think about this sub-ensemble as the mixture of the state in that ensemble, we can describe this sub-ensemble as this mixed state. And the discrimination of sub-ensemble can also be considered as the discrimination of this state, which is the mixtures in the sub-ensemble, probability mixtures in the sub-ensemble. So in the first place, we can think about the ensemble consisting of the state, which is the mixtures of the sub-ensembles. Then we're going to discriminate which state is prepared from this ensemble, epsilon L. Okay? So this is another way to describe the discrimination of sub-ensemble as a quantum states. Okay? So we have this situation. First, we have L4 ensemble, epsilon tensor L. From that, we can think about another ensemble, epsilon L, which consists of sub-ensembles in quantum mixed state representation. Okay? Then, guessing the weight of the index vector C from this L4 ensemble is equivalent to, say, discrimination of the state from this ensemble epsilon L. Okay? So, any question so far? I'm just wondering, am I clear with this equivalence? Okay, fine. Yep.
Can you please once more repeat how discriminating sub-ensemble is related to discriminating states?
So ensemble, probability ensemble is another representation of mixed state. Yeah, so if you don't do any measurement and the preparation of a state with certain probability is nothing but the state of mixed, nothing but the mixed state. So yeah. Okay. So now let's think about how we can discriminate the sub-ensembles only by using LOCC measurement, which is the PL of epsilon L. Epsilon L is the ensemble of, ensemble consisting of the sub-ensembles in mixed state representation, okay? And so for two-state ensemble, if the epsilon has only two states, then we can have this closed form for QG of epsilon L. If you remember, QG is always an upper bound of PL for any ensemble. Okay? So if we think about the ensemble epsilon parenthesis L, the relation still holds. And we can have the closed form for for QG. If the state epsilon has only two, if the ensemble epsilon has only two states. Okay? Yeah, the closed form is related with the actual QG of epsilon. Okay? And moreover, we can also show that if PL is equal to QG, then PL of epsilon L is also equal to QG of epsilon L. Okay? But in more general cases of ensemble, we can have an upper bound of this QG of epsilon L. So we can have an upper bound. Actually, this is also an upper bound of PL. It's an upper bound of an upper bound. Okay? So anyway, so it's bounded above by these terms, 1 over n plus these extra terms. So here, what we can note is the following. If the term here inside the parenthesis is less than 1, then it will vanishes when L increases. Okay? And the vanishing is quite exponentially fast with respect to L. So we have this relation. So PL of epsilon L is always bounded below by 1 over n, which is nothing but just random guessing. It's bounded above by QG, and we have this upper bound of QG of epsilon L, which is of this form. So if this one vanishes, then the low bound and upper bound are just same, 1 over n. That means, so if QG epsilon is less than 2 over n, that means the term inside this parenthesis is less than 1, then the PL of epsilon L will converge to 1 over n as L increases. And you can also see that the convergence is quite exponentially fast with respect to L. So in other words, if we just do LOCC measurement, we can't really do anything to discriminate which sub-ensemble is prepared. Okay? Because the discrimination of epsilon parenthesis L is nothing but the discrimination of the sub-ensembles. Okay? So the data hiding, quantum data hiding is based on this idea. So for any ensemble, epsilon, if PG epsilon is 1, that means if we use global operation, we can have a perfect discrimination. That means the states in these ensembles are orthogonal to each other. Okay? And if QG epsilon is less than 2 over n, which is the condition here, then we have this result. So PG of epsilon and L is also 1. Because we can think about the tensor product of orthogonal state, which is again orthogonal state. So the PG of epsilon L is 1, and PL of epsilon L tends to 1 over n as L increases. Okay? So globally, we can perfectly discriminate which state is prepared, but locally, we can't even guess even the index of the state to be prepared. So the data hiding scheme, the actual data hiding scheme is like this. So first, the hider will prepare a state from epsilon. Let's say row C1 with the probability after C1. And he will share this to Alice and Bob, who's going to recover the data. Okay, and Hyder will repeat this L times, so that on the Lth repetition, the prepared state is row CL, okay, with the corresponding probability after CL, okay. And as mentioned before, this whole procedure can be also considered like this. From this Alford ensemble epsilon times L, Hyder will prepare a state row C and share this to Alice and Bob, okay. And to hide a classical data X, an array classical data X, the hider first evaluate the weight of this index of the shared vector, shared state, okay, which is y, which will be denoted as y, and z is nothing but the addition of this x and y, and modulo n. Okay, then the hider will broadcast this data z to Alice and Bob. Okay, once this z is broadcasted, it's the guessing y is equivalent to guessing x. Or the other way, guessing x is equivalent to guessing y. Okay? But to guess y for Alice and Bob, it's like this. To guess which data y, sorry, let me make it clear. To guess the data y, Alice and Bob needs to discriminate which subensemble is prepared. Okay? And as we've seen before, for the case when the QG epsilon is less than 2 over n and PG epsilon is 1, then PG of epsilon parenthesis L is 1. So globally, we can, Alice and Bob can perfectly discriminate which state is prepared. But locally, they can do nothing but just random guessing. As this one, asymptotically, this one tends to 1 over n. Okay, that's the scheme of the data hiding. And so when am I supposed to finish this?
So 25, no, because it started 10 minutes later.
Okay, 25, I have enough time. Okay, so let's see some examples. The first example is the two-state ensemble. So it can be constructed like this. For any NPT quantum state sigma, so that the trace of the partially transposed, I mean the absolute value, I mean the singular values of the partially transposed state is always larger than 1, strictly larger than 1. Okay? Because this is NPT, if we take the partial transpose, there must be some negative eigenvalues, and together with the positive eigenvalues, the trace will be preserved. So if you think about the sum of the singular values is strictly larger than 1. Anyway, so because this is strictly larger than 1, we can have this two-state. Okay? So row 0 is defined like this, and row 1 is defined like this. And simply just multiplying these two together, you can see that they are orthogonal to each other. Okay? So the PG epsilon is 1 because they are orthogonal. And from theorem 1, because this is a two-state ensemble, we have a closed form for QG epsilon. And QG epsilon parenthesis L as well. It's nothing but the probability of the first state, row 0. Okay? And this is, because this is strictly larger than 1, you can see that this is strictly less than 1. Okay? So for the case when n is 2, this 2 over n is 1. Okay? So it fits to the condition of our data hiding. So by using this two state, you can just repeat sharing this state to Alice and Bob. Then you can reliably hide the classical data. And another example is in higher dimension. So this is the case when n is equal to 2 to the m. Okay? We think about, so f here, curly f means the flip operator in 2QD system. And here, so 1 here means the identity operator. 1 plus minus this f divided by some scalars. These two, so depending on the sign here, They are called the PPT and MPT Werner state in 2QD systems. They are orthogonal to each other. Okay? And then we think about the M-port tensor product of these two states so that they can be represented in this way. Okay? For each I, here BK of I means that if you think about I in the binary representation, M bit binary representation, BKI means the kth digit of the binary representation. So if you think about the M4 tensor product of these two, all of them can be represented this way, in this way. Okay? And for the probability, we can think about the product of the denominator here to get some distribution, and then we normalize the distribution to obtain the probability distribution. Then we're going to use that probability distribution together with the state as the ensemble. Okay? And because these two are orthogonal, we can simply see that PG of epsilon is 1. Yeah, globally, we can perfectly discriminate which state is prepared. And moreover, from the proposition 1 means the equivalent condition for the optimal measurement for QG, if you remember. So we can just check, we can just construct a measurement, optimal measurement, and to show that the QG of epsilon is this value, which is also bounded above this. So to make QG epsilon less than 2 over n, so D needs to be larger than these values. Okay, so for these cases, the ensemble here satisfies that PG epsilon is 1 and QG epsilon is less than 2 over n. So we can use this ensemble to do quantum data hiding. Okay. So this is the graph of the upper bound of QG epsilon L, which is non-upper bound of PL epsilon L for some parameters M, N, and D. Okay. Although, so we consider the case when N is 2 to the M, we don't really need to use all of the state. So if N is less than 2 to the M, we can just use the first N state to do the same analysis. Okay, so these are the graphs of the upper bound. As you can see, they vanishes. I mean, they converges to 1 over n, completely random, quite fast. Okay, so you can just repeat it like 4 or 5 times to get enough randomness. Okay. Right. To summarize, so in this talk we have established a relation between bipartite quantum state ensemble, non-local quantum state ensembles, and quantum data hiding, and provided a sufficient condition with respect to this QG epsilon. Okay, for an orthogonal quantum state ensemble, if this QG epsilon is less than a certain value, then the ensemble can always be used to do quantum data hiding. Okay? And possible future work we can think about here is that, because this is a sufficient condition, we can also think about necessary condition. And if it's possible, we can make a relation with this QG so that we can have some operational meaning of QG with respect to this quantum data hiding. And another thing we can think about here is that because we only talked about bipartite quantum state discrimination, but data hiding can be done in more general scheme. For example, if there are 3 people and 2 of them can collaborate to recover the data. So that we can think about possible quantum data hiding scheme in multi-party quantum systems. Okay? More than 2 parties by using this kind of non-local quantum state ensembles. Okay. Right, so okay, I guess that's all for today. And lastly, there are some open positions available in our group for postdocs and graduate students. So if you are interested in these topics, please let me know. I guess that's it. Thank you.
Thank you very much for the nice talk. We have time for discussion, questions, comments.
thank you for the interesting talk. So I would like to ask you about, so when you consider the LOCC measurement, so is there any limitation of the number of communication between Alice and Bob or not?
Not really.
No.
So you can do even infinite times of round. So actually, this when I talked about LOCC measurement here, I also consider the closure of the LOCC measurement, the limit points as well.
So my question is, so when you restrict the number of communication, so the convergence rate when we take L into the infinity should be fast or not? So this is my.
So intuitively, it should be faster. Because you just limit the number of communication. That means you have more restriction on your measurement. But I'm just saying intuitively. I haven't checked yet.
I see. Okay. Thank you very much.
Any other question? So I have a very naive one. Maybe my brain hasn't started working yet. So when you do data hiding and you consider the many copy case, so are you like kind of encoding the same data and then sending the parties more and more states, or you can encode more and more bits?
Oh yeah. So instead of encoding like data in higher dimension, you can just repeat bits several times. Is that your question?
Yes.
Right. Actually, it's a very good question. So according to our scheme, if you want to share several bits, you need to do like L copies sharing several times to Alice and Bob. And for the case of Alice's, she can maybe do the joint measurement between the first L copy and the second L copy to get some more information. But it's not considered in our scheme. That's why we did consider the higher dimensional data hiding. Yeah.
Thank you. Okay. So if there are no more questions, we can thank the speaker once more.
Thank you.